Hello, my dear dreamers and wanderers, and welcome to Hafee Sleep, where the mysteries of the universe are your lullaby. Whether you're just starting your day, winding down for a peaceful night, or somewhere in the quiet hours in between, you are so very welcome here. Tonight, we're going on an incredible journey together. We're going to travel over 90 million miles, not to a distant galaxy, but to the very heart of our own solar system. We're going to do the impossible and touch the sun. This is the story of the bravest little spacecraft ever built, the Parker Solar Probe, and its daring mission to solve the secrets of our star. If you find your mind drifting into the cosmos with us, if you love getting lost in a great story, then consider making Hafee Sleep a part of your daily ritual. Subscribing is the best way to never miss a journey. And if you're enjoying our trip toward the sun, please give this video a like. It helps our little channel shine brighter in the vast universe of content. Most importantly, we love hearing from our community of cosmic voyagers. It's amazing to think that this story is being listened to all over the world. So, let us know in the comments. Where are you watching from, and what time is it for you right now? Are you cozying down for sleep, or is this your morning inspiration? We read every single comment and love connecting with you. Now, find a comfortable spot, relax your mind, and let's begin. Have you ever, on a perfectly clear day, stepped outside, felt the sun on your face, and just for a moment, been struck by a thought so simple yet so profound that it almost takes your breath away? That great, brilliant ball of fire in the sky, the very heart of our solar system, the giver of light and life. What is it really? We see its light, we feel its warmth, but it remains in so many ways a magnificent mystery, a raging inferno of plasma and power that we gaze upon from the safety of our distant rocky world. It's familiar, yet utterly alien. For all of human history, the sun has been a subject of worship, of study, of art and poetry, but never of touch. It is the one constant in our sky that we could never truly visit, never truly know. It is, by its very nature, untouchable, or at least it was, because humanity, in its relentless and beautiful curiosity, decided to do the impossible. We decided to build a machine, a messenger, a robotic explorer brave enough to journey into the sun's fiery embrace and send its secrets back to us. We decided to touch the sun. And we gave this daring mission a name, the Parker Solar Probe. Now, before we dive into the incredible mechanics of this spacecraft, let's set the stage properly. So let's really sit with that idea for a moment. We look up every day and see this glorious, steady, brilliant disk in the sky. It's so constant, so reliable, that it's easy to think of it as just there. A fixed feature of our universe, like a lamp in a ceiling. But my goodness, that is such an understatement. If we could pull back the curtain, if we could see the sun not just as a ball of light, but for what it truly is, we would behold the most spectacular, violent, and energetic phenomenon in our entire neighborhood. It is not a calm ball of fire. Fire is a chemical reaction. What's happening on the sun is something else entirely, something on a scale so grand it's almost impossible to fathom. It is a star, our very own star, and it is alive with ferocious activity. Think of it not as a ball of fire, but as a giant, churning, seething nuclear reactor suspended in space. But even that doesn't quite capture it. The stuff it's made of isn't a gas like the air we breathe, not in any state we're familiar with. It's so incredibly hot that the very atoms that make it up get torn apart. Under normal circumstances, an atom is a neat little solar system, a nucleus of protons and neutrons at the center, with electrons whizzing around it in orbits. But on the Sun, the heat is so intense that these atoms are violently smashed together. The electrons are ripped right off, leaving behind a chaotic, bubbling soup of naked atomic nuclei and free-flying electrons. This chaotic, charged soup is what scientists call plasma. It's often called the fourth state of matter, beyond solid, liquid, and gas, and it behaves in strange and wonderful ways, especially under the influence of magnetic fields, which the Sun has in abundance. And where does all this insane heat come from? It all starts in the very heart, the core of the Sun. Picture this, a place so dense, so incredibly squeezed by the immense weight of the entire star above it, that the pressure is unimaginable. The temperature here isn't thousands of degrees, but millions of degrees. About 15 million degrees Celsius, to be a bit more precise. In this unimaginable pressure cooker, something magical happens. The hydrogen atoms, which are the simplest and most abundant element in the universe, are moving so fast and are pressed so close together that they can't avoid smashing into each other. When they collide, they don't just bounce off, they fuse. This is the process of nuclear fusion. 4 hydrogen nuclei are fused together to create one helium nucleus. Now, here's the truly incredible part, the bit that still feels like magic, even when you understand the science. When that fusion happens, the new helium nucleus actually weighs a tiny, tiny bit less than the 4 hydrogen nuclei that made it. So, what happened to that missing mass? It didn't just vanish. According to a fellow named Albert Einstein, mass and energy are 2 sides of the same coin. His famous equation, E = mc squared, tells us that a little bit of mass, m, can be converted into a colossal amount of energy, E, because it's multiplied by the speed of light, c, which is a huge number, squared, which is an astronomically huge number. So that tiny, tiny bit of lost mass is transformed into a staggering burst of energy. This is the secret of the Sun's power. It's a continuous, controlled hydrogen bomb going off billions of times every second. And it's that energy, born from lost mass, that powers the entire star and gives us all life on Earth. But that energy doesn't just zip right out from the core to the surface. Oh no, that journey is an epic saga in itself. The energy, in the form of intensely powerful photons of light, is born in the core. But the core is surrounded by an incredibly dense zone, called the radiative zone. It's so thick and crowded with plasma that the photon can't just travel in a straight line. It's like trying to walk in a straight line through a packed, raging mosh pit at a concert. The photon gets absorbed by an atom, re-emitted, bounced around, zigzagging, taking one random step after another. Scientists estimate that a single photon of light might take tens of thousands of years, yes, thousands of years, to finally drunkenly stumble its way through this radiative zone. It's an incredibly slow, random walk outwards. Once it finally reaches the outer third of the Sun, the journey changes. This next layer is called the convective zone. Here, the plasma is still super hot, but it's a little less dense. This allows it to behave like a pot of boiling water or oatmeal on a stove. The plasma at the bottom of this zone gets heated up, becomes less dense, and rises in massive, bubbling cells towards the surface, carrying the heat with it like a conveyor belt. Once it gets to the surface, it cools down slightly, becomes denser, and sinks back down to be heated up again. These convection cells are enormous, some as large as the entire state of Texas, and they are constantly churning and bubbling. It is this churning motion that we can sometimes see as granulation on the sun's surface, a sort of speckled pattern, like the skin of an orange, if that orange was made of living, boiling fire. Finally, after its journey of thousands of years, the energy bursts forth from the surface. This surface is called the photosphere, which literally means the sphere of light. This is the part we actually see, the bright disk in the sky. It's what we think of as the surface of the sun, even though it's not a solid surface at all. Just the depth at which the sun's plasma becomes transparent enough for light to escape into space. And it's hot, unimaginably hot by our standards, about 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. Hot enough to instantly vaporize any rock, any metal, any material we know of. This light, which has been on such a long and arduous journey, now races across the void of space at, well, the speed of light. And it covers the 93 million miles to Earth in a little over 8 minutes. So, the sunlight that warms your face on a nice afternoon left the surface of the sun just 8 minutes ago. But the energy within it began its journey deep in the core before human civilization even began. Now, here is where the story gets really weird, and where scientists started scratching their heads. If you stick your hand in a fire, it gets hot. When you pull it away, the air around it is cooler. It makes sense. The heat source is the hottest point. So, you would naturally assume that the farther you go from the sun's surface, the cooler things would get, right? Well, the sun loves to break the rules, because immediately above the photosphere, things actually get hotter. It's the greatest, most baffling paradox in all of solar science. Just above the visible surface is a thin reddish layer called the chromosphere. During a total solar eclipse, if you have a good eye, you can sometimes see it as a faint reddish rim around the blacked out sun, a ring of fire. It's hotter than the surface below it, but that's just the beginning. Beyond the chromosphere, stretching out for millions of miles into space, is the sun's magnificent outer atmosphere, the corona. This is the part we were talking about, the crown. And this crown is made of an incredibly wispy, thin, superheated plasma. During a total solar eclipse, when the moon perfectly blocks the blinding light of the photosphere, the corona is revealed in all its glory, a beautiful, pearly white, ethereal halo with streamers stretching outwards. It is one of the most breathtaking sights in all of nature, and it is mind-bendingly hot. While the surface below is a cool 5,500 degrees Celsius, the corona routinely simmers at between 1 and 3 million degrees Celsius. Let's just sit with that again. The sun's atmosphere is hundreds of times hotter than its surface. It's as if you walked away from a campfire, and a few feet away, the air suddenly became thousands of degrees hotter than the flames themselves. It makes no sense based on our everyday experience. This is the coronal heating problem, and it has been a monumental puzzle for astrophysicists for nearly a century. Where is this immense heat coming from? How is it being pumped into the corona? The energy from the core can't directly explain it. The rules of heat transfer just don't work that way. Something else must be happening, and the prime suspect is the sun's powerful and complex magnetic field. But the corona isn't just sitting there, being mysteriously hot. This incredibly hot plasma is so energetic that the sun's gravity can't hold on to it. This superheated gas is constantly boiling off, streaming out into the solar system in all directions. This is the solar wind. The name makes it sound gentle, like a soft breeze, but that's a serious misnomer. This is not a wind, it's a hurricane. A supersonic hurricane of charged particles, mostly protons and electrons, blasting outward at truly terrifying speeds. By the time this wind travels the 93 million miles and reaches the vicinity of Earth, it's still moving at anywhere between 250 and 750 kilometers per second. That's over 1,000,000 miles per hour. This relentless wind blows past all the planets, far beyond Pluto, defining the very boundaries of our solar system and creating a giant protective bubble around us called the heliosphere. This solar wind is the sun's way of reaching out and touching everything in its domain. When this wind interacts with Earth's own magnetic field, it creates the beautiful dancing lights of the auroras, the northern and southern lights. It's a beautiful, harmless side effect. But the solar wind also has a darker side. The sun isn't always calm. It has moods. It has storms. There are events on the sun, like solar flares, sudden intense flashes of radiation, and coronal mass ejections, CMEs, which are massive bubbles of plasma and magnetic field that are thrown off the sun's surface. These events send out particularly strong and fast gusts in the solar wind, like a typhoon mixed with a radiation storm. When these gusts slam into Earth's magnetic field, they can cause geomagnetic storms. These storms are beautiful for aurora watchers, but they are a serious threat to our modern technological way of life. They can induce extra electrical currents in power grids, overloading them and causing massive blackouts. They can fry the electronics on multi-million-dollar satellites, knocking out communications, GPS, and weather forecasting. They also pose a serious radiation hazard to astronauts in space who are outside the protective shield of Earth's atmosphere. Understanding and predicting this space weather is becoming increasingly critical. And to truly predict it, we can't just study it from here as it passes by. We need to go to the source. We need to travel to the place where this wind is born and accelerated to such incredible speeds. We need to dive into the heart of the mystery itself, into the superheated, beautiful, and dangerous corona. And that, of course, is a job for a very special, very brave robot, a probe named Parker. And that, right there, is the grand overarching mission of the Parker Solar Probe: to trace the flow of energy that heats the corona and accelerates the solar wind, to determine the structure and dynamics of the plasma and magnetic fields at the source of the solar wind, and to explore mechanisms that accelerate and transport energetic particles. In simple terms, it was sent to answer two fundamental questions. Why is the corona so hot? And how is the solar wind accelerated to such incredible speeds? To answer these questions, we couldn't just observe from afar. We had to send a detective right into the scene of the crime. It's a wonderful thing, the imagination of a scientist. Long before we had the tools, we had the dreams. The dream of going to the sun, of literally touching a star, is one that has captivated astronomers and engineers for generations. The very first official whispers of such a mission began all the way back in 1958, the same year NASA itself was born. Think about that for a moment. This was the era of slicked back hair, big-finned cars, and the very first primitive satellites beeping their way around Earth. The space age was just a newborn, and yet here were these visionary thinkers staring up at the sun and saying, "We should go there." It's a breathtaking leap of ambition. But of course, back then it was pure science fiction. The report might as well have said, Step 1, invent magic. The technology to make it happen simply didn't exist, not even close, because the challenges involved are, to put it mildly, monumental. They are the kind of problems that make an engineer wake up in a cold sweat. Let's break them down. First, and most obvious, the heat. How on Earth, or rather, how off Earth, do you build a machine that can get close enough to literally fly through the sun's atmosphere without that machine instantly turning into a puff of metallic vapor? We're not talking about oven temperatures here. We're talking about an environment where temperatures can reach millions of degrees. What material could possibly withstand that? How do you shield delicate electronics, the brain of the spacecraft, from being fried to a crisp? Then there's the radiation. The sun is a blizzard of not just light and heat, but also high-energy particles. This radiation can play havoc with computer systems, corrupting data and causing malfunctions. A spacecraft going into that neighborhood needs to be hardened like a digital fortress. But perhaps the most counterintuitive challenge of all is simply getting there. This one really twists your brain. We all have this instinctual idea that getting to the sun should be easy. I mean, it's right there. It's huge and powerful, and its gravity is constantly pulling on us. It feels like if you just pointed a ship at it and turned off the engines, you'd just fall right in, like a rock dropped from a cliff. But space doesn't work like that. This is the orbital paradox, and it's the key to understanding why this mission is so brilliantly clever. To understand why going to the sun is so hard, you have to understand what orbit really is. Let's use a simple analogy. Imagine our sun is the center of a merry-go-round, and Earth is a person standing near the outer edge. Now, that merry-go-round is spinning incredibly fast. How fast? Well, Earth is whipping around the sun at a speed of about 30 kilometers every single second. That's 67,000 miles per hour. We are, all of us, on this planet, moving at 67,000 miles per hour sideways. We don't feel it because it's constant, and there's no air resistance in space to buffet us, but that's our orbital speed. It's this tremendous sideways speed that keeps us from falling into the sun. Our planet is in a perfect, perpetual balance between the sun's gravity pulling us inward and our sideways motion trying to carry us away in a straight line. The result is a graceful, circular dance that has continued for billions of years. Now, imagine you're that person on the edge of the spinning merry-go-round, and you want to get to the central pole. What do you do? If you just try to step directly towards the center, what happens? Your body still has all that sideways momentum from the spin. You wouldn't go straight to the pole. You'd go flying off on a tangent, stumbling in a curved path. To get to the center, you have to slow yourself down. You have to counteract that spinning motion by walking against the spin, fighting your own momentum. The slower you go relative to the spin, the closer to the center you'll get. It's exactly the same with a spacecraft leaving Earth. When a rocket launches, it doesn't just point at its target and go. It first has to escape Earth's gravity, which it does by achieving what's called orbital velocity. But once it's in orbit around Earth, it's still part of the bigger system. That spacecraft is, by default, also moving around the sun at the same 67,000 miles per hour as the Earth is. It's on the same merry-go-round. So, if you want to send a probe to the sun, to have it fall closer to that central pole, you have to cancel out almost all of that sideways orbital speed. You have to make it stop going so fast around the sun. And that takes an insane amount of energy. To cancel out Earth's orbital velocity, you would need a rocket roughly 55 times more powerful than the one needed to get the same spacecraft just to Mars. It would have to be colossal, the size of a skyscraper, and impossibly expensive. It's like trying to stop a speeding bullet by shooting another bullet directly at it. the force required is immense. For decades, this simple physics problem is what made a solar mission seem impossible. A direct plunge was completely out of the question. They needed a smarter way, a more elegant way, a way that used the universe's own forces to do the heavy lifting. And they found it. The solution is a beautiful cosmic trick called a gravity assist, and the key to pulling it off was our sister planet, Venus. A gravity assist is sometimes poetically called a gravitational slingshot, but for this mission, it's less of a slingshot and more of a brake, a planetary brake. Here's how it works in this case. Instead of fighting Earth's orbital speed head-on with a giant rocket, the Parker Solar Probe was launched with that speed. It was sent on a path that would take it flying towards Venus. Now Venus is also orbiting the Sun, a little slower than Earth because it's closer to the Sun. As the probe approaches Venus, it falls into the planet's gravitational pull. From the perspective of someone on Venus, the probe would swing around the planet and fly away again. But because Venus itself is moving through space around the Sun, the interaction is much more complex. It's like throwing a tennis ball at the front of a moving train. The train imparts some of its energy to the ball, speeding it up. But for Parker, the engineers wanted to do the opposite, slow the probe down. So they designed the flyby so that the probe would pass behind Venus in its orbit. As the probe swings around the planet, Venus's gravity tugs on it, but because the probe is passing behind, the overall effect is that the planet's gravity steals a little bit of the probe's orbital energy, slowing it down relative to the Sun. Think of it like this. You're on that merry-go-round again, and you're skating along on roller skates. You're moving at the same speed as the platform. You want to slow down to get to the center. So you grab the arm of a friend who is standing a little closer to the center and moving a little slower. As you zip past them, you hold on for just a moment. Their slower speed pulls on you, slowing you down just a bit. You let go, and now you're moving slower relative to the merry-go-round, so you naturally drift inward toward the center. That's exactly what Parker does with Venus. It uses the planet's gravity as a brake. And it doesn't just do it once. The entire mission is a masterclass in patience and precision. The probe will perform this maneuver not once, not twice, but 7 times over nearly 7 years. Each time it flies by Venus, it gets another gentle gravitational tug, slowing it down a little more, allowing the Sun's gravity to pull its orbit a little tighter, a little closer. With each pass, the point of its closest approach to the Sun, called perihelion, drops lower and lower. It's like a diver circling a drain, with each circle bringing them closer to the center. This incredibly clever use of orbital mechanics means the mission requires a fraction of the fuel it would need otherwise. It trades time for fuel, using the natural gravity of a planet to do the work that would otherwise require an impossibly large rocket. This is the elegant solution that transformed the mission from a 1950s daydream into a 21st century reality. It's a reminder that sometimes, to solve a seemingly impossible problem, you don't need brute force. You need to be clever. You need to work with the universe, not against it. You need a cosmic dance partner. And for the Parker Solar Probe, that partner is the cloudy, mysterious world of Venus. Now, let's talk about the star of the show, the spacecraft itself. The Parker Solar Probe is a technological marvel, a testament to human ingenuity in the face of extreme adversity. It's roughly the size of a small car, about 3 meters tall and a couple of meters across, but its design is dominated by one crucial, groundbreaking component, the Thermal Protection System, or TPS. You and I would call it the heat shield. This isn't just any heat shield. This is the most advanced heat shield ever built. It is the probe's guardian, its parasol, its suit of armor that allows it to survive in the hellish environment so close to the sun. At its closest approach, the probe will be just 6.16 million kilometers, or about 3.83 million miles, from the sun's surface. To put that in perspective, Mercury, the innermost planet, is about 36 million miles from the sun at its closest. The Parker Solar Probe will be 7 times closer than Mercury. At that distance, the intensity of sunlight is about 475 times greater than what we experience here in orbit around Earth. The heat shield will face temperatures approaching 1,370 degrees Celsius, or 2,500 degrees Fahrenheit, hot enough to melt iron, and far hotter than the surface of Venus, the hottest planet in our solar system. So, how do you build something that can withstand that? The engineers at the Johns Hopkins Applied Physics Laboratory, who designed and built the probe for NASA, came up with an ingenious solution. The heat shield is a lightweight, sandwich-like structure. Its front face, the part that always faces the sun, is made of a superheated carbon-carbon composite. It's a material that is incredibly strong and can maintain its integrity at extreme temperatures. But the real magic is in the core of the shield, a 4.5-inch thick layer of carbon foam. Yes, foam. This carbon foam is about 97% air. It's an excellent insulator, and its primary job is to block and absorb the intense heat, preventing it from conducting through to the spacecraft bus, the main body of the probe, which is tucked safely in its shadow. The beauty of this design is that while the front surface might be glowing at 2,500 degrees Fahrenheit, the back of the shield and the spacecraft behind it will be sitting at a relatively balmy room temperature around 30 degrees Celsius or 85 degrees Fahrenheit. The instruments and electronics can operate in a comfortable shirt-sleeve environment, all thanks to this incredible technological umbrella. But the heat shield isn't just a passive piece of armor. It's a critical part of the probe's guidance and control systems. For the shield to work, it must always be pointed directly at the sun. If it were to tilt even slightly, the full fury of the solar furnace would spill onto the unprotected spacecraft body, frying its systems in seconds. To ensure this never happens, the probe is equipped with a series of sophisticated sensors called solar limb sensors. These are tiny windows on the side of the heat shield's shadow. They are designed to detect even the faintest hint of sunlight. If a sensor detects light, it means the spacecraft is beginning to drift out of alignment, and it immediately triggers a correction. The probe's attitude control system, a set of small thrusters, will fire to nudge the spacecraft back into the perfect position, keeping the precious body and its instruments entirely in the umbra, the deep shadow of the shield. It's a constant, automated dance of detection and correction, a life-or-death balancing act performed millions of miles from any help. Of course, a heat shield alone doesn't make a scientific mission. The whole point is to gather data, and for that, the Parker Solar Probe is packed with a suite of 4 incredibly sophisticated instrument suites, each designed to work in tandem to paint a complete picture of the sun's outer atmosphere. These instruments are the eyes and ears of the mission, and they had to be specially designed to not only survive the heat, but also to take measurements without being fooled or damaged by the intense environment. Let's meet them. First, there's fields. This isn't one instrument, but a suite of them, and its job is to measure the electric and magnetic fields around the spacecraft. Think of it as the probe's sense of touch, for the invisible forces that dominate the solar environment. It consists of several long antennas that stick out beyond the protective shadow of the heat shield. These antennas will directly measure the waves and turbulence in the solar wind plasma, and they will map the structure and strength of the sun's magnetic field, which is believed to be the engine behind much of the corona's heating and the solar wind's acceleration. These measurements are crucial because we think magnetic fields are the key to unlocking the sun's secrets. The sun is a giant magnetic dynamo, and its twisted, tangled field lines are thought to snap and reconnect, releasing immense amounts of energy in the process, energy that could be heating the corona and propelling the solar wind. Next, we have the SWEEP investigation, which stands for Solar Wind Electrons, Alphas, and Protons. This is the probe's particle counter. SWEEP's job is to catch and analyze the solar wind itself. It has special cups, called Faraday cups, that are pointed directly into the solar wind to scoop up particles and measure their velocity, density, and temperature. One of these cups, called the Solar Probe Cup, is a particularly brave little instrument. It actually protrudes beyond the heat shield, exposed directly to the full solar intensity. It's made of materials like titanium, zirconium, molybdenum, and sapphire tubes that can survive the extreme heat, and it's actively cooled. This cup is literally tasting the solar wind right from its source, counting the protons and electrons that stream past the spacecraft at hundreds of kilometers per second. The data from SWEEP will tell us exactly what the solar wind is made of and how it behaves as it leaves the sun. Then there's the WHISPER instrument, the Wide Field Imager for Solar Probe. This is the eyes of the mission. WHISPER is a set of 2 telescopes that take traditional images of the solar corona and the solar wind. But its view is unique. Instead of looking directly at the sun, which would instantly damage its cameras, it looks sideways, out from behind the heat shield, capturing the structure of the corona and the solar wind as they flow past the spacecraft. It's like looking out the side window of a car driving through a snowstorm. You can see the patterns and swirls of the snowflakes. WHISPER provides context for the other measurements. It shows the large-scale structures like coronal streamers and CMEs, or coronal mass ejections, that the probe is flying through, allowing scientists to connect the in-situ measurements from fields and SWEEP, the measurements taken right at the spacecraft, with the actual visual features of the sun. Finally, there's the ISO-IS instrument. This stands for Integrated Science Investigation of the Sun. Its focus is on the most energetic particles, the solar energetic particles that are accelerated to nearly the speed of light during solar flares and other eruptions. These particles can be dangerous to technology and astronauts, so understanding how and where they get their incredible speed is a key goal. ISOIS uses 2 separate instruments to measure these particles across a wide range of energies, helping us understand the acceleration mechanisms that turn ordinary solar particles into high-speed bullets. Together, these 4 instrument suites work in harmony. Fields measures the magnetic highway. SWEEP counts the traffic flowing down that highway. WHISPER takes pictures of the road and the landscape. And ISOIS studies the dragsters and race cars that scream past everything else. It's a complete scientific toolkit for dissecting the solar atmosphere. So, after decades of dreaming, years of designing, and countless hours of engineering genius, the moment finally arrived. On a warm Florida morning, August 12, 2018, the Parker Solar Probe was no longer just a set of blueprints and dreams. It was a real, tangible spacecraft, fueled up and secured atop one of the most powerful rockets ever built, the Delta IV Heavy. This rocket is a beast, a monster of raw power. It looks like three giant rockets bolted together, and for good reason. It needed every ounce of thrust it could muster for this unique mission. And even that wasn't quite enough. Tucked on top was a secret weapon, a third-stage rocket motor. This was the final kick, the extra boost needed to send our solar traveler on its precisely calculated path. The launch from Cape Canaveral was a spectacle of fire and thunder, a perfectly executed beginning to an epic voyage. It roared into the sky, a spear of light aimed not just at the stars, but at the very heart of our solar system. Its first destination wasn't the sun, though. Not directly. Remember that clever plan to use Venus as a brake? This is where the mission's beautiful orbital dance began. After a few months cruising through space, the probe had its first date with Venus in October of 2018. This wasn't a mission to stop and explore Venus. It was a high-speed flyby, a graceful gravitational pirouette. As it swooped around the planet, Venus's gravity reached out and, just as planned, gave the probe a gentle but firm tug backwards, relative to its orbit around the sun. It was like a cosmic cop pulling over a speeding car, slowing it down just a tad. This tiny slowdown was all it took. The sun's gravity, always pulling, now had a slightly stronger grip. The probe's orbit, which was initially a wide loop similar to Earth's, tightened up. Its path became more elliptical, like a stretched-out rubber band, bringing its closest approach to the sun, a point called perihelion, much, much nearer. And this was just the first step. This is the patient, repetitive genius of the mission plan. The Parker Solar Probe doesn't get a one-time ticket to the inner solar system. It's on a subscription plan for Venus flybys. Over its 7-year primary mission, it will perform this exact maneuver 6 more times. Each encounter with Venus is another tap on the brakes, another chance to shed a bit more of that orbital energy we talked about, another step inward in this grand, spiraling descent towards the sun. With every pass, the orbit shrinks, the ellipse tightens, and the perihelion point dips deeper and deeper into the sun's hellish outer atmosphere. It's a mission of extraordinary patience. We're talking about years of travel and gravity assists before it finally reaches its ultimate, record-shattering, closest approach. But with every loop, it's been sending back data, and with every loop, it's been making history. Almost immediately, it began smashing records. The first major milestone was claiming the title of closest human-made object to the sun. The previous record was held by a plucky little German-American spacecraft called Helios 2, which had held the crown since April of 1976. Think about that for a second. The record had stood for over 42 years. That's a testament to how incredibly difficult it is to get close to the sun. Helios 2 had gotten to within a respectable 27 million miles of the sun's surface, a magnificent achievement for its time. But Parker blew right past that mark without even breaking a sweat on its very first close approach. It wasn't even at its final destination yet. It was just on its first few orbits, and it was already diving closer than any spacecraft in history. And with each subsequent Venus gravity assist, it will shatter its own record again and again until it ultimately gets a mere 3.83 million miles from that fiery surface. To put that in perspective, that's less than 1/10 the distance between the Sun and Mercury, the innermost planet. It's a realm of space that has never been explored, a true frontier. But the record for proximity isn't even the coolest one. The Parker Solar Probe also became the fastest human-made object ever relative to the Sun. Speed, in orbit, is a direct result of your distance from the gravitational body you're orbiting. The closer you are to a massive object like the sun, the faster you have to travel to avoid falling into it. It's a balancing act between gravity's pull and your forward momentum. So, as Parker's orbit pulls it closer and closer to the sun on each pass, it is whipped around at ever-increasing, mind-numbing velocities. It has already screamed past the sun at speeds exceeding 150 kilometers per second. Let's just sit with that number for a minute. 150 kilometers in a single second. That translates to an almost incomprehensible 330,000 miles per hour. How fast is that, really? Well, at that speed, you could travel from New York City to Los Angeles in less than 20 seconds. You could zip from the Earth to the Moon in under half an hour. You could fly from Washington, D.C. to Tokyo, a journey that takes a commercial jetliner over 14 hours, in less than 60 seconds. It's a velocity so far beyond our everyday experience that it feels like it belongs in a superhero comic. And just like the distance record, this speed record is temporary. On its final closest orbits, the Parker Solar Probe will be traveling at a truly staggering 430,000 miles per hour. That's fast enough to spot a sign on the side of a highway and be 100 miles away before you've even finished reading it. It will be moving at roughly 0.064% the speed of light. This incredible speed isn't just for bragging rights. It's a necessary part of the mission. It allows the probe to quickly dart through the most dangerous, intense regions of the corona, sampling the plasma and measuring the fields before the extreme heat has too much time to impact the spacecraft. It's a high-speed surgical strike into the heart of the inferno. And through all of this, the blistering speeds, the searing heat, the little spacecraft has to keep itself safe. Its survival depends entirely on its revolutionary heat shield, the thermal protection system, always staying perfectly positioned between the spacecraft's body and the sun. This is a constant, automated ballet of precision. The probe can't wait for commands from Earth, which can take over 10 minutes to arrive each way. By the time an engineer on the ground saw a problem and sent a correction, it could be far too late. So, Parker has to think for itself. It's equipped with a set of brilliant sensors called solar limb sensors. These are like tiny, highly sensitive eyes peeking out from the edge of the heat shield's shadow. Their only job is to look for sunlight. If even a single photon of direct sunlight touches these sensors, it's a 5-alarm fire. It means the spacecraft has drifted slightly out of alignment. The sun is peeking around the shield. When this happens, the probe's autonomous system doesn't hesitate. It immediately commands a series of small thrusters called attitude control thrusters to fire. These tiny puffs of cold gas gently nudge the entire spacecraft back into the correct position, ensuring the main body remains entirely within the deep, cool shadow of the shield. It's a constant process of minute adjustments, a dance of fire and shadow performed entirely by the robot itself, millions of miles from home. This is the incredible balancing act that allows Parker to do its science. Tucked safely in its own shadow, the spacecraft's body enjoys an almost room temperature environment, a serene pocket of tranquility just a few feet away from temperatures that could melt steel. From this safe haven, it extends its instruments out beyond the shield to taste the solar wind, feel the magnetic fields, and capture images of the corona it's flying through. It's a masterpiece of engineering, a testament to human ingenuity, and it's out there right now, dancing with a star, rewriting the textbooks, and sending its secrets home. But of course, breaking records was never the real point. The speed and distance titles are just flashy headlines, the kind of thing that grabs the public's imagination. and rightly so. But for the scientists huddled over their computer screens back on Earth, huddled in labs and universities around the world, the real prize, the true treasure, has been the data. The endless streams of ones and zeros, the measurements and readings, the images and particle counts that Parker has been faithfully sending back across the vast gulf of space. This is the payoff. This is why we spent decades and billions of dollars. And let me tell you, even from its early orbits, when it was still getting itself situated in its new solar neighborhood, the probe started sending back information that has fundamentally and profoundly shaken our understanding of the sun. It's as if we've been trying to understand the nature of a vast, stormy ocean by only ever studying the gentle waves that wash up on a distant shore. Parker is the first submarine diving deep beneath the surface, and it's discovering that the deep ocean is far stranger and more turbulent than we ever imagined. One of the very first and most head-scratching discoveries came from the field's instrument suite, the one designed to measure the invisible magnetic and electric forces around the spacecraft. Scientists expected the solar wind, as it flowed away from the sun, to be relatively smooth and uniform at its source. They knew it became turbulent and gusty by the time it reached Earth, but they assumed that was from interactions during its long journey. Parker's measurements revealed something completely different. The solar wind, right from its birthplace, is incredibly dynamic and structured. It's not a smooth river. It's a raging whitewater rapid filled with whirlpools and eddies and sudden violent surges. And the most dramatic of these features are the things scientists have playfully named switchbacks. Now, that's a fantastic name, isn't it? It sounds like something from a hiking trail or a railroad track. And that's exactly what they are. Imagine the sun's magnetic field as a series of lines, like railway tracks extending out into space. The solar wind, made of charged particles, is like a train that is locked onto these tracks, flowing along them. Now, imagine you're watching one of these magnetic railway tracks, and suddenly, for no apparent reason, a section of it does a complete, sudden, and dramatic 180-degree U-turn. It flips back on itself, forming a giant S-shaped kink before snapping back to its original direction. That's a switchback. The particles riding this magnetic track are suddenly whipped around in this giant chaotic loop, reversing direction for a moment before carrying on. From the perspective of the Parker Solar Probe, it's as if the magnetic field suddenly screams past the spacecraft, pointing in exactly the opposite direction for a few seconds or minutes, before just as suddenly snapping back to normal. These things are not rare, delicate little things. They are massive, common, and pack a powerful punch. They can be tens of thousands of miles long, and during some of Parker's passes, the spacecraft was practically swimming in them, with switchbacks happening one after another after another. It's a constant, frenetic flipping and snapping of the magnetic field. Nobody predicted this. It was a complete surprise, and their origin is still one of the biggest mysteries the mission is trying to solve. Where do they come from? What cosmic process on the sun has enough energy to literally tie the magnetic field into these giant, sudden knots and then launch them out into space? Some theories suggest they might be caused by jets of plasma erupting from the sun's surface. Others think they might be generated by magnetic reconnection events, where magnetic field lines break and reconnect in a different configuration, releasing a tremendous amount of energy. There's even a fascinating idea that they could be caused by the turbulence within the solar wind itself, like waves crashing into each other and creating these strange, rogue magnetic waves. Why do we care about these weird magnetic hiccups? Because they might be the missing piece of the coronal heating puzzle. Remember that multi-million-degree corona? Scientists have long suspected that the energy to heat it must come from the churning magnetic field at the sun's surface. But how does that energy get transferred and deposited into the corona? One leading theory is that it's done via waves or nanoflares, tiny explosions on the sun. But these switchbacks present another tantalizing possibility. Each one of these magnetic kinks represents a huge release of energy. As they form and then snap back into place, they could be dumping enormous amounts of energy directly into the solar wind plasma, like whipping a rope and sending a wave of energy down its length. This energy dump could be what superheats the corona and gives the solar wind its incredible acceleration, like a series of constant magnetic slingshots firing particles out into the solar system. Parker's job is to trace these switchbacks back to their source, to see where they are born and how they behave. They might seem like a bizarre curiosity, but they could very well be the engine that drives the entire system. And that's not the only surprise Parker found on its initial forays. Let's talk about something completely different. Dust. It sounds boring, right? After all the talk of million-degree plasma and magnetic fields, dust seems mundane. But in space, dust is everywhere. Our solar system is filled with a thin, thin cloud of fine dust particles, leftover crumbs from the formation of the planets billions of years ago. For a long time, scientists have had a theory that close to the sun, this dust should disappear. The thinking was that the intense heat so near the sun would vaporize any dust particles, creating a region around the sun called the dust-free zone. It was a clean, theoretical idea. But the universe is rarely so neat and tidy. Parker, with its sensitive instruments and its unprecedented access, has been able to study this dust population like never before. And what it found is not a sudden, clear boundary where the dust just stops. Instead, it's seeing a very gradual, steady thinning of the dust. The closer it gets to the sun, the fewer dust particles it detects. It's like driving into a gradually thickening fog that then very, very slowly starts to clear the deeper you go. This is a fascinating finding. It tells us that the process is more complex than simple instant vaporization. The dust particles might be getting smaller and smaller, gradually sublimating away over distance rather than hitting a magic wall and vanishing. This might seem like a small detail, but it's critical for understanding the environment near the sun and the life cycle of material in our solar system. For the Parker spacecraft itself, it's also crucial engineering data. Even tiny dust particles, when you're hitting them at 330,000 miles per hour, can pose a risk. Each impact, even with a microscopic grain, is a high-speed event. Understanding the density of this dust helps engineers understand the wear and tear on the spacecraft over its long mission. This is the beautiful, iterative process of science. We don't just send a probe and get all the answers in a neat package. We send it, and it answers the questions we thought to ask. But more importantly, it reveals new phenomena we never even dreamed of, like the magnetic switchbacks. It confirms some of our theories, like the gradual dust reduction, but in a more nuanced way than we expected. Each orbit, each dive into the corona, is like turning on a light in a dark, unexplored room. We might have had an idea of what the furniture looked like from feeling around in the dark, but now we can see the strange patterns on the wallpaper, the odd artifacts on the shelves, the unexpected doors leading to even more rooms. Parker is our light. It's showing us that the sun's environment is not a placid, predictable place. It is a dynamic, chaotic, and wildly energetic arena, filled with strange magnetic structures and gradual gradients of cosmic dust. And with every new piece of data, we are not just getting closer to the sun, we are getting closer to understanding the fundamental forces that shape the very space around us. According to the current status, the probe has completed its 24th close approach to the Sun on June 19, 2025, achieving its closest distance of 3.8 million miles, 6.2 million kilometers, and matching its record speed of 430,000 linear 690,000 kph. This marked the final planned close approach of its baseline 7-year mission, which began with its launch on August 12, 2018. The primary mission included 24 orbits around the Sun, utilizing 7 Venus gravity assists to gradually shrink its orbit and bring it closer to the Sun. As of now, the spacecraft remains healthy and continues to operate normal. While the baseline mission concluded with the 24th perihelion, NASA plans to formally review the mission's next steps in 2026. Depending on the spacecraft's health and fuel levels, the mission could be extended indefinitely until power degradation or other factors render it inoperable. Notably, the probe has significantly more fuel remaining than initially anticipated, potentially allowing for years of additional operations. This extension would enable further exploration of the Sun's corona during the declining phase of the solar cycle, which historically features extreme space weather events. End-of-life scenarios for the probe. The probe uses thrusters for attitude control and trajectory adjustments. Once its hydrazine fuel is depleted, it will no longer be able to maintain the precise orientation needed to keep its heat shield facing the Sun, leading to overheating and system failure. The probe relies on solar panels for power, but over time, exposure to the Sun's intense radiation and dust in the inner solar system will gradually reduce their efficiency. When the panels can no longer generate sufficient power to operate instruments or communication systems, the mission will effectively end. As systems fail, the probe will be unable to transmit data or receive commands from Earth. Mission operators will eventually lose contact, leaving the spacecraft to drift silently in its orbit. Unlike missions that orbit Earth or other planets, the Parker Solar Probe cannot be placed into a stable graveyard orbit. Instead, its orbit will naturally decay due to gravitational interactions, causing it to spiral closer to the Sun over centuries. Eventually, the probe will succumb to extreme heat and radiation, vaporizing and becoming assimilated into the solar wind. Project scientist Noor Rawafi poetically described this fate. The probe will become part of the solar wind itself. The Parker Solar Probe's mission is expected to conclude gradually between 2026 and beyond, depending on fuel and power levels. Its ultimate fate, disintegration in the Sun's environment, symbolizes a fitting end for a mission dedicated to unraveling the mysteries of our star. In the world of science, and especially in the often anonymous world of robotic space exploration, missions usually get functional, descriptive names. Think Mars Reconnaissance Orbiter, or Solar and Heliospheric Observatory. They tell you what the machine does. They are practical, but they lack a certain heart. They don't often honor the people whose dreams and intellect made the mission possible in the first place, and when they do, it's usually a posthumous tribute, naming a spacecraft after a giant of the past, like Galileo or Cassini. But the Parker Solar Probe is different. It carries a name that is deeply personal, profoundly meaningful, and in a beautiful break from tradition, it was bestowed upon it while the man it honored was still very much alive to see his dream take flight. This decision, to name humanity's first mission to To Touch a Star after Dr. Eugene Newman Parker is one of the most poignant and fitting tributes in the history of science. It's a story that adds a deeply human layer to this incredible technological achievement. To understand why this is so special, we have to travel back in time to the 1950s. The field of solar physics was very different then. We knew the sun was there, of course, and we were beginning to understand its nuclear heart. But the space between the planets was largely thought to be just that: empty space, a pristine vacuum. The idea that the sun was constantly breathing out a torrent of particles was considered by many to be borderline nonsense. It was into this scientific landscape that a young, brilliant astrophysicist at the University of Chicago named Eugene Parker stepped. Through his intricate calculations and his deep intuition about how magnetized plasmas behave, he began to piece together a radical theory. He postulated that the sun's million-degree corona couldn't possibly be static. Such a hot, tenuous gas, he reasoned, must expand outward, blowing past all the planets in a great continuous stream. He gave this theoretical stream a deceptively simple name: the solar wind. When he tried to publish his groundbreaking paper in 1958, it was met with instant skepticism and outright ridicule from some of the top minds in the field. The peer reviewers, the gatekeepers of scientific publishing, rejected it. They said his ideas were preposterous. One reviewer famously declared that the paper was absurd and that Parker should, and I quote, "go to the library and read up on the subject before he tries to write a paper about it." Can you imagine the audacity? Here was a brilliant thinker, armed with math and physics, being told he simply didn't know what he was talking about. It was a classic case of a radical new idea challenging a deeply entrenched old guard. It's a story that has played out throughout the history of science, from Galileo to Darwin. The establishment resists, but Eugene Parker had a powerful ally: the legendary editor of the Astrophysical Journal, Subrahmanyan Chandrasekhar, another giant of science, who himself had faced skepticism for his work on black holes. Chandrasekhar saw the merit and the courage in Parker's work. He overruled the reviewers and published the paper. It was a brave act that changed the course of space science. Even after publication, the criticism was fierce. Parker later recalled giving talks where senior professors would stand up and literally laugh at him. But he stood by his math. He had the quiet, unshakable confidence that comes from knowing your calculations are sound. And then, just a few short years later, vindication arrived from the cold, hard vacuum of space. In 1962, NASA's Mariner 2 spacecraft, on its way to Venus, carried instruments that were capable of detecting this theoretical solar wind. And it found it. It was there, just as Parker had predicted, a constant supersonic flow of plasma from the sun. The laughter stopped. The skeptics were silenced. Eugene Parker, once a subject of ridicule, was now recognized as a visionary. His 1958 paper became the foundation for an entirely new field of science: heliophysics, the study of the sun and its influence on the solar system. Every single mission to study the sun, every textbook chapter on the solar wind, every prediction of space weather, all of it rests on the shoulders of his courageous work. For decades, the dream of sending a probe into the solar wind, of going to its very source, was known simply as the Solar Probe mission. It was a concept, a goal. But as the mission moved from the drawing board toward reality, the scientists and engineers working on it felt strongly that it deserved a better name. A name that reflected its profound purpose. They wanted to honor the man whose intellectual curiosity had paved the way. In 2017, in a move that was unprecedented in NASA's history, the agency announced that the mission would be renamed the Parker Solar Probe. It was the first time a NASA spacecraft had ever been named after a living person. The announcement was a moment of incredible, emotional closure. For Dr. Parker, then 90 years old, it was the ultimate validation. It was the scientific community, once his biggest critic, now saying, "You were right. Your life's work matters so much that we are naming our most daring journey after you." He was able to travel to Cape Canaveral and witness the launch of his namesake spacecraft in August 2018. He described it as an emotional moment. Imagine that feeling. To see a colossal rocket carrying a billion-dollar machine designed specifically to answer the questions you first posed 60 years earlier, thunder into the sky, bearing your name. It's a moment of pure, unadulterated poetry. And the gift of time allowed for one final, beautiful, full-circle moment. Dr. Parker lived long enough to not only see the launch, but to also see the first data stream back from the probe. He got to see his theoretical solar wind, the thing people once laughed at him for, become a real, tangible, and wonderfully complex thing, measured in exquisite detail by the spacecraft that carried his name. He saw the first evidence of those strange switchbacks, the magnetic zigzags that are now a central mystery of solar physics. He witnessed the very beginning of the revolution he had started so long ago. He passed away in March 2022, but he left knowing that his legacy was secure, forever sailing through the solar wind he discovered, racing toward the sun. He dedicated his life to understanding. The name Parker Solar Probe is therefore so much more than a label. It is a story. It's a story about the courage to be wrong and the greater courage to be right when everyone says you're wrong. It's a story about the long arc of scientific progress, where a single idea can germinate for decades before finally blooming into a mission of exploration. It connects the past, present, and future of space science. Every time we say its name, we are not just identifying a spacecraft. We are paying tribute to the human spirit of inquiry. We are honoring the quiet theorist at his chalkboard, whose imagination reached out into the void and felt the solar wind long before any machine could. The probe is our machine, our tool, our extension. But its soul, its namesake, is a reminder that all these incredible journeys begin not with metal and fuel, but with an idea. And sometimes, the most important thing we can do is have the courage to give that idea a name and then build a ship to carry it home. And so, as our brave little messenger continues its silent dance with a star, we're left back here on Earth, looking up at that same familiar light with new eyes. It's no longer just a bright disk in the sky, but a dynamic, living, breathing world of fire and mystery. A world we are now, in a very real way, touching. The story of the Parker Solar Probe is a testament to human curiosity, to our endless desire to reach beyond the possible and understand the universe we call home. It's a story that reminds us that even the greatest mysteries are not forever out of reach. If this journey into the heart of our solar system brought a little wonder to your day, or a little peace to your night if it made you think, or better yet, if it helped you drift gently into sleep, then we've done our job here at Hafee Sleep. We truly hope you'll join us for our next adventure. Subscribing to the channel is the easiest way to make sure you don't miss it. And if you enjoyed this, please do give it a like. It helps us more than you know. Before you go, we'd love to hear from you. This community is built on shared curiosity from every corner of the globe. So drop a comment below and tell us, Where in the world are you listening from? And what time is it there? Are you dreaming among the stars or just beginning your day? From all of us here at Hafee Sleep, thank you for listening. Be kind to your mind, get some rest, and we'll see you next time. Sweet dreams.